I am Vijay Kumar S. Biradar, working as HOD, General Science and Engineering at NB Noble Singhad College of Engineering, Solapur, with 19 years of experience. Today we are going to discuss the subject Control System 2 for TE Electrical Engineering, and the topic that we are going to discuss now is state observability. The state observability will consider a plant represented in state space with the two equations x dot is equal to ax plus bu and y is equal to cx, and the plant model is represented diagrammatically below with u as input, b as the relation of these input signals or input variables to the x, then a as the relation of the first derivatives of all the state variables to the state variables, and y is related to x with the help of this matrix C. And these matrices A, B and C are all constant matrices. So this system represents a linear time invariant control system. The definition of this state observability is that a system is said to be completely observable if every state variable of the system affects some of the outputs. In other words, I'll say that it is often desirable to obtain information of state variables from the measurement of inputs and outputs. That means by measuring the inputs and outputs, we can obtain the state variables of the system. If it is possible to obtain or determine the state variables, its state from its initial to final state, if it is possible, then we say that the system is observable. That means we can observe the system state variables. The state variables basically represents the parameters, values of the system, how they are behaving to a particular input, and these behaviors can be observed within the system itself, and we can check the output because of these variations observed in the system state variables. If any of the state cannot be observed from the measurement of the output, the state is said to be unobservable, and the system is not completely observable or simply unobservable. That means if it is not possible to measure the outputs with the state variable, then we can say that it is unobservable. All the state must be observed through the measurement of the output. That means output equations should have all the state variables which are relating to the output, either one or other output variables. Then we'll see in this figure that the linear system in where the state variable x2 is not affecting the output, or output cannot be connected to the state variable x2, therefore the x2 state is not observable, whereas x1 is related or it is connected to the y, therefore only x1 is observable and x2 is not observable. When we talk about the overall system, the overall system is not completely observable. For the system to be completely observable, it is necessary and sufficient that the observability matrix OM, that is, we are going to determine analytically with the help of this observability matrix. If that observability matrix has a rank of n, where n is the order of system, then we say that the system is completely observable. The rank of that observability matrix must be equal to n, and this rank of observability matrix is obtained by getting the determinant of this matrix. If the determinant of observability matrix is non-zero, we say that the rank of observability matrix is n, therefore the system is completely state observable. If the determinant of observability matrix is 0, that means the system is not completely observable or it is unobservable. This is the observability matrix given by the Kalman, and the observability matrix represents the rows. N rows will be there, and every row consisting of the vector C, or the next is the multiplication of c into a, then c into a square, like that. We have a rows where we are going to represent the vectors of those matrices, that is observability matrix, as C, Ca, Ca square up to Ca raised to n minus 1. This is the observability matrix for the system whose order is n. The system is said to be completely state observable if the rank of this observability matrix is equal to n. So we'll see the example for a better understanding of this concept of observability. Consider the system given below. X dot is equal to 0, 1, 0, minus 2, x plus 0, 1 u, and y is equal to 0, 4 x. So this x dot is related to x with the matrix A, the x dot is related to u with the matrix B, this y is related to x with the matrix C. The observability matrix is obtained as this system is second order system, that means only 2 by 2 matrix is there, therefore it is a second order system. If it is 3 by 3, it is a third order system. So as it is second order system, we need to consider only two rows. So the first row is C, second row is CA in the observability matrix. So we'll calculate the values here. C is 0, 4, it is given in the system representation, and we'll take the multiplication of C and A. So this C is 0, 4 and A is 0, 1, 0, minus 2. So what we need to do here is the matrix multiplication. The first matrix is of order 1 by 2, the second matrix is of 2 by 2. So the resultant matrix will be 1 by 2. That is the first row of first matrix and the column of second matrix. That is, it is 1 by 2. So we are going to multiply 0 with 0, it is 0, 4 into 0, 0. Then in second column, it is 0 into 1, 0, and this 4 into 2, it should be minus 8 it is. Okay, so make the correction there, it is minus 8. Therefore the observability matrix can be written as observability matrix is equal to 0, 0, and here it is 4 and minus 8, it should be minus 8. So that correction is required, you can do that. When we get the determinant of this matrices, this observability matrix determinant is equal to 0, which represents that the rank of this observability matrix is not equal to n, that is 2. Observability matrix is less than 2, therefore the system is not completely state observable. For this particular system, it is not completely observable as one of the column. By saying towards the observability matrix, one can say that this column is having 0 value, and here it is 4 and it is minus 8, therefore it is a linearly dependent matrix will be there, one can say it in mathematical language. But for our understanding, it is the rank of this matrix, when we calculate, it is 0 into 12, so the rank of this or the determinant of this matrix will be 0, which indicates that the rank is not equal to 2, therefore the system is not completely state observable. Here we can see the signal flow graph of this particular above example, where we can observe that this y is not related to x1, it is not connected to x1, this y is connected to x2, therefore this x1's state is not observable, whereas this x2 state is observable because it is connected to the output y. This can also be observed from this signal flow graph. Here, by this diagram, we can have the clear idea of controllability and observability. These state variables are representing with the system, and here it is the input u and output y. For controllability, this u is related for the first case, that is 1 upon 1 s plus 1. For this particular system, this u is related to x1, so it is having a control, so we can control this x1 with the help of this u, therefore this system is controllable. This y is connected to x1, therefore it is also observable, that means we can measure the state variable x1, therefore it is observable. So the first system is controllable as well as observable. For second system, when I